All right. Now this unit and the next unit is going to be closely tied to the periodic table once again. Notice how a common theme throughout our whole class has been the periodic table. We started off very, very simple. We started with just organizing it, and then we started with layering it in a two-dimensional fashion, starting with common elements that shared chemical characteristics, et cetera. Well, and then we got into the electronic configuration, which again shared electronic configurations, similarities. And today we're going to be getting into more of the quantitative aspect to the periodic table. Okay, so some of these terms we've already talked about, and we're going to get into them in significantly more depth. Okay, there's a common term called atomic mass. And what that is a while back, 120-ish years ago, we had to figure out a way to reference compounds in terms of their mass. And we chose originally oxygen, and then we went to carbon. Carbon being a more, oxygen is a good candidate because we have an oxygen atmosphere, but carbon is more of a fundamental building block. So the powers that be, the United International Chemists of Applied and Pure Chemistry, decided on using carbon as a base. So they based everything on the isotope carbon-12. Now, if you remember, carbon-12 has got 6 protons, 6 neutrons. It exactly weighs 12 units. Now, when I say units, a unit is a proton is either a proton or a neutron, not electrons, because electrons are 1/300,000th of the mass of either a proton or neutron. So we're looking at mass numbers, looking at protons and neutrons. Okay, so the mass number or the atomic mass of a particular isotope has to do with the number of protons and neutrons added together. And that'll give us an atomic mass. Okay. And notice that atomic mass is not an integer down here, it's a decimal. That's because the atomic mass represented in the periodic table represents all the isotopes of a particular element. In this case, we're looking at, for example, carbon. Carbon has got a atomic mass of 12.01, not 12. That means there are other isotopes contributing to that average atomic mass. And that has to do with the naturally occurring isotopes of carbon, which involve there's a lot of them. All those together average 1201. Okay, so that's why that's a decimal number. So the atomic mass is always a decimal number if there are multiple isotopes available for that particular element. Notice, let's clean this up here. Notice boron is 10.81. That means there are some boron 10s, boron 11s, boron 12s, boron 9s. An average of all those isotopes occurring naturally, is 10.81. And this is rounded to the second decimal point. On this particular periodic table, everything is rounded to the second decimal point. Now, I'm going to show you some differences here. Notice these guys. Okay. Those aren't decimals. That's because those are particularly stable and they exist only in a particularly stable isotope. The rest of the isotopes are so unstable that they're not around long enough to even count. That's why, one, it's an integer, and two, it's in parentheses. All man-made isotopes are in parentheses because they were only made specifically for a certain type of neutron-proton configuration or a certain isotope. For example, plutonium-244. There are other isotopes of plutonium, but this is the one that's they originally made, and that's what went on the periodic table. Okay. So, for example, and also let me the units of atomic mass. There are two units of atomic mass. One is AMU, atomic mass units, or U, and also grams per mole. So what is the atomic mass of magnesium? We would zoom over here to magnesium, which would be 2431. And again, that would be AMUs or U's or grams per mole. I'm going to talk about this grams per mole bit in a little while. Okay, so the atomic mass of any of these, you just look at the decimal number on the periodic table. Okay. There's something called a formula unit. The formula unit is the ratio of the elements and their number. So carbon dioxide, for example, formula unit for carbon dioxide would have 1 carbon. You remember the ones are optional, and 2 oxygens. So if you look at the atomic mass of carbon, it's 1201. Each oxygen is 16.00. So that means this is 32. So 32 plus 1201 is 44.01. And that would be U's, AMU's, or I'm going to keep throwing in this grams per mole because we're going to be getting to that. Okay. So when we look at a molar mass or a formula mass for ammonium nitrate, it's going to be, well, how many nitrogens do I have? Well, I have 2. How many hydrogens do I have? I have 4. How many oxygens? 3. So if we add those all up, it's going to be 80.04. AMU, or grams per mole. And all we're doing is we're taking the formula and adding up its constituent parts, adding up the molar mass, the molar mass or atomic mass of its constituent parts. So in this case, we have 2 carbons, we have 6 hydrogens, and we have 1 oxygen. 4601. Units, AMUs, or grams per mole. Okay, so you're going to be looking up these numbers all the time in Unit 4, all the time, and in Unit 5 as well. Okay, so basically, we just add up its parts. We add the decimal numbers from the periodic table and add up the parts. And that'll be the formula unit, or the mass of molecules, or the molar mass. Now, I mentioned mole already. And what is this concept? Okay, whenever we're working with an industry, there are units associated with the industry that are common. For example, if I raised chickens for eggs, I would be talking in terms of dozens, mega dozens, et cetera. But the basic unit is going to be the dozen, because we always talk about a dozen eggs. That's the egg industry. If we're talking about the paper industry, we're talking about ream, which is 500 pages. Like a ream of paper, it's 500. If we're talking about cars, if you're selling cars, what's the unit of a car? Well, it's each. So we have a favored unit per industry. When we're in the science industry, that is chemistry, physics, biology, and that's mostly molecular biology, geology, engineering. The convenient unit there is mole, which comes from molecule. Okay, so the mole is the unit, the convenient, I want to stress, it's the convenient unit in chemistry. And the reason why it's a convenient unit is because atoms are so incredibly small. Molecules are incredibly small. When things are small, the unit gets bigger and bigger. Now think about going back to okay, we start off with eggs. Eggs, you can put an egg in the small part of your palm, and we have 12 per dozen. Paper is really light, so there are 500 pages per ream. Cars are really, really big, so we're talking about 1, okay, or each. When things get smaller and smaller and smaller, the convenient unit tends to get bigger and bigger. That's why our unit in chemistry, physics, molecular biology, geology, engineering is the mole, because in those disciplines, we're talking about atoms and molecules, and atoms and molecules are small, so we want to use an appropriate unit, and that unit is mole. And that unit is, instead of 12, 500, whatever, it's 602 times 10 to the 23rd. And this is 3 sig figs. This can go out to, 8 sig figs or whatever. Normally we refer to it's 602 times 10 to the 23rd. Normally it's going to be 3 sig figs. So, and by definition, we always refer to carbon isotope 12. There are 6.02 times 10 to the 23rd atoms of carbon 12 in 1 mole. And this, when we talk about grams now, we're talking about the molar mass as opposed to the formula mass or molar mass, okay? So there's molecular mass, formula mass. Those are AMUs. We talk about molar mass. Those units are grams per mole. Okay, so what is the molar mass for carbon dioxide? Okay. That is so if you look up carbon on the periodic table, it's 12.01 grams per mole. Oxygen is 16 grams per mole. If we add that up, we end up with 4401 grams per mole for carbon dioxide.
Can I ask something?
Sure.
I understand that these are different units, but would mole still equal to an atomic mass unit, just like the examples that we previously went over?
Say again.
So just like this is 44.01 grams per mole, it would still be 44.01 atomic mass units.
Yes, it would. That's right. That's right.
So they're equal.
They're equal. Yes. So whenever you, exactly. Wonderful question. Okay. So it depends on what we're talking about here. If we're talking about a molecular mass or formular mass, we're talking about AMUs. Now, AMUs aren't particularly useful, but molar mass is very useful. Because then we're talking about some grams and stuff, and you can really be very useful. Okay, so, but yes, your question is exactly right. The grams per mole is the same as AMUs or A's, or excuse me, or U's. Okay, that was your question, right?
Yes, that was. Thank you so much.
Perfect. Okay. All right, and that is a very common. It's kind of one is a theoretical question, which is this up here. You know, this formula mass thing, and this is a practical one. Grams per mole is very practical because you're going to be talking about grams per mole a whole bunch from now to the end of the semester, a whole bunch. We're not going to be talking a lot about AMUs because you really can't do much with AMUs has to do with an individual molecule. Well, we don't work with individual molecules. We work with huge amounts of molecules and elements and atoms. So the AMU works great for if you're talking about one compound, one atom, or whatever, of an element. But when we get it to real mass, we need to talk about grams per mole, and that comes from the decimal number from the periodic table. Okay, so I'm going to move this guy. Yeah. Okay, so we've got, I want to take an aside here, okay? Okay, we've just talked about a couple of things here. We've talked about molar mass. Molar mass the units are grams per mole. That means that is a conversion factor, grams per mole. It depends totally on the compound. Yeah, carbon dioxide is 44.01 grams per mole. Oxygen gas is 32.00 grams per mole. So it depends on compound. Okay. And where do you get that information from? Periodic table. So the periodic table feeds into that. Okay, so we have a new conversion factor in our cadre of conversion factors. We have the molar mass, grams per mole, and because it's a conversion factor, we also have moles per gram. And it's always per 1 mole. Okay. Secondly, how many units are in a mole? Now this could be atoms, or it could be molecules. It doesn't matter. 6.02 times 10 to the 23rd is a unit. Just like doesn't have to apply to eggs. It could be dozen sheep, it could be dozen students, it could be a dozen atoms. Same with moles. Excuse me. Moles are just a unit. So we can talk about a mole of atoms, a mole of molecules, a mole of sheep, a mole of cars. Mole is just a number. So 6.02 times 10 to the 23rd per mole. Or when I say atoms, I also mean molecules. But remember, it's a unit. It's counting how many. Whenever you think of, when I ever ask you questions, how many atoms, how many molecules, how many whatever, I want you to think Avogadro's number. The guy that discovered this number is Avogadro. So Avogadro's number is 602 times 10 to the 23rd. Now that's a huge number. That is 6 with 21, that should be 6 with 23 zeros after it. That's a huge number. That tells you how small atoms and molecules are. Okay, so we've gone down to the point here. So we're talking about the mole as the unit in chemistry when we're dealing with compounds and we're dealing with elements. Mole. Okay, how many are in the mole? 6.02 times 10 to the 23rd. Now, depending on the compound, it's going to weigh differently. That's why all these numbers are different from the periodic table. Excuse me. For example, if we had a bowl of 20 apples, we had 20 grapes. The number is the same. Do they weigh the same?
No.
Exactly. Why?
Well, because apples are bigger. They usually weigh more.
Exactly. That's why when we talk about a mole of a chemical, it weighs something different because each chemical is not the same as another chemical. Just like apples are not the same as grapes. So we have 20 apples. That does not equal 20 grapes as far as for weighing them. What if we had a mole of apples and a mole of grapes? Would they be the same?
No.
No, exactly for the same reason. Apples are bigger than grapes. So if you have a mole of apples, it's going to weigh a heck of a lot more than a mole of grapes. Just like 20 apples are going to weigh more than 20 grapes. So 20 carbon dioxides is going to weigh more than 20 oxygen gases because it's an apple and a grape. They aren't the same thing because carbon dioxide has a carbon and 2 oxygens, where oxygen gas has 2 oxygens. They aren't the same animal. Hence, they don't weigh the same. Does that make sense?
Yes, it does.
Okay, all right. So we are going to get back into Unit 1 kinds of problems. All of you are going like, oh my God, Ferguson, are you kidding me? That again? Yes, unfortunately. Okay. So we have a conversion factor here. And of course, as a conversion factor, we always have the inverse. So that's 602 times 23rd, 1 mole. Same here. Okay, so if we have 3 moles of carbon, how many atoms do we have? How many atoms? Remember I said whenever we have counting, how many? Think of Avogadro's number. So whenever we see any of these, whenever you see how many, think Avogadro's number. Because we're counting them. How many? In this case, how many carbon atoms are there in 3.0000 moles of carbon? Okay, well, what's going back to remember our standard deal. What's given? What are we calculating? And what's the setup? Okay, so what's given here?
The mole number is given to us.
Exactly. So we have zeros. Is that like 7 or something like that? 7 there. And what are we calculating?
The number of carbon atoms.
Yeah. Okay, so remember counting Avogadro's number. So we're going to multiply that by we want the given to always cancel. That means it's on the bottom. So now our answer is going to be 3 times 602 times 10 to the 23rd. How many sig figs is our answer going to have?
3.
Ignoring that. Yeah, because that's 3 sig figs. That is 8 sig figs. So our answer is going to have 3 sig figs. So we're going to now multiply. Get my calculator out, but I should have gotten out earlier. Yeah, so we're going to multiply 3 times 602. So that's going to be 1.81 times 10 to the 24 atoms. Okay, so we have 3 sig figs. Now notice the way this is, I did not set this problem up. This was done by another colleague. They added this in, which I think is a nice touch. I think it adds clarity. Yeah, notice those cancel as well. We have a mole of calcium atoms here, carbon atoms. And carbon atom, oops. We have carbon atoms canceling, leaves us with 602 times 10 to the 23rd times 3 total atoms. Now notice here we started with moles. Rarely do you start with moles. Usually you start with something else that you need to convert to moles. So we can start with grams. We can talk about gaseous liters. We can talk about concentration. Whatever we're starting with, whatever, convert to moles, because everything revolves around the concept of moles. So in this case, we're starting with 5 grams of gold. Let's just go over here. And how many? It's what? 4. Okay. Wait, oops. 5 grams of gold. How many atoms of gold are there? Okay. Well, do we have a conversion factor between grams and the number of atoms? Where are our conversion? No, we don't. We have moles in the number of atoms. And we also have conversion from grams to moles. We have 2 conversion factors now. Okay. One is going to be grams and moles. The other is going to be atoms or molecules in moles. Now in this case, we've got to convert first to moles. And how many grams are in a mole of gold? Gold is right here. Okay, 196.97. Okay, so for each mole of gold, there's 196.97 grams. Gold is very heavy, very dense. Okay, once our grams are canceled, we now have moles of gold. Now we need to convert that into atoms of gold through Avogadro's number conversion factor. And again, we want moles to cancel. And what are we left with? Atoms. So we started with grams. We wanted to end up with number of atoms. So the setup is going to be do with parentheses this time. Leaves us with atoms. Now we just need to grind that baby out. So it's going to be 5 times 602 EE 23 divided by 196.97. Okay, that gives us 1, 2, 3. And okay, so there's a lot of these kind of problems, and I've given you extra worksheets. If you look on modules, you'll see extra worksheets doing these kind of problems. You need to do lots of these problems. What's given, what are we calculating? Setup. It's given, calculating, setups, and always consider significant figures. Always. Okay. Yeah.
May I ask a quick question about the problem we just did?
Mhm, mhm.
So when you wanted to know how many grams of gold there was in 1 mole, you referred to the atomic mass unit.
Yes.
So
Yes, exactly.
okay,
Which should be
so
right here.
okay, so does that mean that each atom has a different number of grams per mole? So
Yeah.
1 mole of, is that what you meant when you said that they're different? So 1 mole of gold is not the same as 1 mole of hydrogen.
Yes, exactly. Just
Okay.
like a dozen apples is not equal to a dozen grapes. Why? Because the apple has more stuff in it than each grape. So if we multiply by 12 of the apples, because there's more stuff in the apples, it's going to weigh more than the grapes, but have less stuff. Does that make sense?
It makes perfect sense. Thank you.
Cool. Yeah, exactly. And the stuff in the atoms is protons and neutrons. Protons and neutrons. So gold has got 79 protons, hydrogen, as your example, has 1. So gold is going to weigh more. Why? Because more stuff. Think of a bag of gold and a bag of hydrogens. Well, for each gold, there's a whole bunch of stuff in it. And it's just going to weigh more. It's got more, a bag of 10 marbles as opposed to 20 marbles. Which weighs more? Well, 20 marbles. Okay. All right. Okay, so here we're starting with give you so many atoms. What does it weigh? Okay, and again, these are all 2-part problems because we have to go through the intermediate of moles each time. Because there is no direct atoms to gold, but there is atoms to mole and moles to gold. Always a 2-stepper here. Okay, all right, let's look at this one here. So we're starting with so many gold atoms. Let's just, instead of using that one, let's just come up with our own. Let's say we had 1.5 times 10 to the 5th atoms of silver. Let's say Ag. What does that weigh? Okay, so when we think about weight or mass, we think of grams. So we're given atoms. We want to calculate grams. So do we have a conversion from atoms to grams? No. We've got to go through our common mole. So we're going to go get it to moles. Once it's in moles, we now can go to grams. Okay. This is standard all chemicals, if we're counting in moles, will be 602 times 10 to the 23rd. All chemicals, no exceptions. Grams per mole is totally it totally depends on the chemical. The formula for the chemical is different each time, so the grams are going to be different each time. But we're counting, just like it doesn't matter if it's a dozen eggs or a dozen sheep, it's still 12. Avogadro's number. Doesn't matter if it's Avogadro's number of atoms or Avogadro's number of sheep. It's still 602 times 10 to the 23rd. Okay, so we have atoms. We want to go to moles. Okay. That gives us moles of silver. How do we get to grams of silver? That's through the molar mass of silver, which is grams per mole. Okay, we find that on the periodic table, which is 107.87 grams per mole. All right, you guys, 107.87, I forgot. So 107.87 grams per mole. That gives us grams of silver. So are these setups looking familiar from Unit 1?
Yes, sir.
Yes, so when you're, we're going to be continuing this idea. Now, this is going to help you tremendously when you have to take physics, because physics is going to be exactly the same thing. And we're talking about meters per second, meters squared per second. You know, it's going to be the same kind of dimensional analysis, same setup. Do the seconds cancel? Do the meters cancel? Same idea. So if you get this down in this class, you'll do well in 400. You'll also do well in your physics class. And if you're an engineer, you'll do well in your engineering class, because all those classes use dimensional analysis, what we're doing here. Okay, so 1.5 times 10 to the 5th times 107.87 divided by 602. Okay, so we're looking at 269. So we have 1.5 times 10,000 atoms. That's a lot of atoms. But look how little it weighs. That's 16 zeros in front of the 2 grams. That's how small atoms are. Okay. These are 4 and 5 are just more examples. You know, what's given in case of water, we have 1.7 moles. And normally we're not working in moles. Normally we're working in grams or milliliters or something like that. Normally we're not working in moles, because you can't go to the store. I want to go to, can you imagine going to Rayleigh's and going down the aisle and saying, where's the water aisle? And they'll say, sir, it's on aisle 4. And you're gonna say, can I buy moles of water over there? You can buy a jug of water. You can buy, probably can't even, if you said, I want to buy, 10,000 grams of water over there, they're going to look at you funny. But you can go over there and buy liters of water, though, all over the place. So let's look at number 5. Excuse me. This is another conversion factor. A gram of water is the same as 1 milliliter of water. And this is by definition, so this has infinite sig figs. So it's 1.00000 grams over 1.00000 milliliters of water, and it's at a certain temperature. Okay? Because volume and mass differ by temperature. But if we round it off to 1 and 1, it's pretty standard. So if you have 500 milliliters of water, that's the same as 500 grams. Okay, so let's do this problem here. Okay, so if I'm drinking half a liter of water, how many molecules of water am I consuming? Okay, so the given is milliliters of water. And our new conversion factor is 1:1 gram mill of water. That's pure water, pure water. Okay, so now we're at 500 grams of water. We can't go from grams to number of molecules directly. We have to go via moles, so we need to know. So the molar mass of water from the periodic table, where we have 1 oxygen, and 2 hydrogens, is 18.02 grams per mole. Okay, that gives us moles of water. And now to convert to molecules of water. And we're not talking about atoms now, we're talking about molecules of water. That's again counting. So that's an Avogadro's number. The abbreviation for molecule is MOLC. MOLC. Now be really careful when you write, because MOLC looks like MOLE. So if you're going to abbreviate molecules, be very careful when you write out the C. Okay, so we have milliliters to grams, grams to moles, moles to molecules. We're going to go 500 times 602 divided by 18.2. And we're looking at, again, 3 sig figs. Okay, that's 3 sig figs here. This is infinite. This is 4 sig figs. This is 3 sig figs. Our answer is going to be 3 sig figs. So that is 1.67. That's 10 to the 25th molecules water. I want to emphasize again. Now, unit 4 is going to be multiple choice, true, false, but unit 5 test is going to be like unit 1 test is. Okay. So just be careful of sig figs now. Okay, so I'm going to end it here. And I want you to practice between now and Monday. I gave you lots. Well, you need to do your tests. Also, let's do Saturday. Minor detail. Try to fit in some practice between now and Monday on this as well. I totally understand if you're overwhelmed with unit 3, trying to get the test in. I'm going to review this on Monday and get into things like, well, if you've got so many atoms of a compound, how many individual atoms of a certain constituent of that compound you have? So I have 5 grams of acetic acid. How many grams of hydrogen do I have in that? Okay, that's where we're going to be going on Monday. All right. So this is all déjà vu from unit 1. Are we all having fun?
Yes.
I'm actually surprised that I'm excited to be back at math. I didn't think that would be my case, but I'm excited for this. It's like, oh, I remember this. Okay.
And again, I want to build on the structure we had from unit 1, the dimensional analysis. And again, I want to emphasize, now, Sally, you're not going to be going on to Chem 400, but many of you, the rest of you are. And you're going to be looking at doing the same dimensional analysis over and over and over again, whether we're dealing with gases, we're dealing with mass, we're dealing with solutions. It's all going to be dimensional analysis. It's really, really handy tool to have in your tool bag. You go into engineering, same thing. If you go into physics, same thing. And we all, within that quantitative discipline, try to teach a very consistent strategy. And I want to focus on strategy in this class. Strategy. What are you starting with? What do you want to calculate? How do you get there? Sally, where's your cat?
Oh, I try to keep them out of my bedroom because then they hide and they won't leave. And yeah, so I just try to keep them out of this area.
Half the time you have your cat around your neck.
Yeah, I'm sure she's at the door waiting.
Okay, everyone. All right. So between now and next week, I need to get your tests in, and then also try to do some problems based on the extra worksheets I gave you besides the main worksheet I gave you. Okay. All right. And don't be shy about emailing me questions. We can do some private Zoom sessions as well. We can do a public session or two or not, getting into between now and next week as well. Unit 4 and 5 are very, very closely related, and that is really the front end of 400. It's really important to get these 2 units down well. So anyway, everyone, take care. We're gonna have some rain. Yay.
Thank you, Professor.
All right, you guys.
I'm sorry. I have a few questions to ask about the test. Should I message you?
What are the questions?
I already took it. It's just that